Welcome to the next in the series of our Asynt webinars. Today we're going to be looking at real-time compact flow UV spectrometry. So thank you all for coming. Today, as I said, we're going to be talking about the impact of Asynt's FlowUV spectrometer, and also highlight some of the research carried out by our guest speakers today from the University of Liverpool. Catherine will put the link for questions in the chat. Feel free to write any questions you have throughout this webinar, and we will have time at the end to answer everyone's questions. If we run out of time in the question and answer session, we'll endeavour to answer everyone's questions over the course of the next coming days. So as I said, we've got two fantastic guest speakers today that's showing some real case studies in their research. So we have Dr. Fergus Parveen and Harry West. So Fergus specialises in flow chemistry, catalysis and sustainable chemical processes. She's currently the manager of the Liverpool Digital Flow Centre, and she's research coordinator with the Slater Group at the University of Liverpool. So her work focuses on the continuous flow synthesis, or on continuous flow synthesis, primarily looking at the development of porphyrins, including telescoped processes. So Harvey is a PhD researcher, also at the University of Liverpool. Harvey specialises in real-time reaction analysis and self-optimizing processes. So his work also focuses on combining flow synthesis with multi-dimensional analytical techniques. And both of our guest speakers will talk about their research in more detail. So before we get on to the real scientific body of this, I just wanted to introduce why we're here. So we're going to be talking about UV vis spectrometry. And UV vis spectrometry simply can be described as when light is absorbed, reflected or transmitted when it strikes an object. That intensity of the absorbed light in the UV and visible spectrum regions is measured using a spectrophotometer, which is what we're talking about. So a reference measurement of the incident light is needed to compare the amount of light that passes through our sample. So this is what we'd call a blank sample. And then our spectrophotometer can determine the concentration of our analytes in the sample by using the Beer-Lambert law, which says essentially that the amount of light absorbed is exactly proportional to the concentration of the sample and the path length. So we can use this in a number of ways to measure the concentration and identify the analyte we're looking at. So we are going to be talking about our fiber optically controlled spectrometer, and there's a real differentiation between fiber optic spectrophotometers and traditional bench systems. But the Asynt FlowUV, as you can see here, is a low-cost full spectrum inline UV vis spectrometer. And it can be used for both batch and flow applications. There's a huge number of sampling devices that we can use coupled to the fiber optics. The firmware and software ensures that the user interface is really quick to learn. It's really intuitive. Both expert users and novices can pick this instrument up and use it straight out of the box within minutes. And as I said, this is really optimized for applications. So if you have an application in flow for continuous analysis, we can handle that. If you just want to do simple batch experiments, we can also supply cuvette holders and other probes for different applications. So we're talking about fiber optically coupled spectrometers, and there's a number of advantages of these. So I'm going to talk about those briefly before we get into the science. So they're compact and portable. They're often smaller than traditional benchtop spectrometers. This means they're good for fieldwork. We can take these anywhere. They can be moved between labs. They're modular and versatile. As I said, it's really easy for us to have different probes for different applications, whether they're immersion probes or flow cells or cuvette holders, as we said earlier. They have real flexibility in remote sampling. So these fibers, the fibers that are coupled to the instrument, the light source and detector, and the sampling device, can measure samples away from the spectrometer. And there's lots of advantages of that: heating, no need for reflectance or whatever. That means we can use them in hazardous environments or inline. We can use them for process monitoring, but we can also put them in the hard to reach locations, which increases the usability. So spectrometers of this time often use array detectors. We have one in our instrument here. That means you have very fast data acquisition. We are constantly monitoring the full spectrum. And with this device, we can monitor from 200 to 1050 nanometers. And we get that full spectrum in milliseconds. So really fast data capture. And we can use this for real-time and in-situ measurements. So flow cells allow us that continuous analysis at any point in the fluidic network. And this is ideal for flow chemistry applications and chromatography and applications such as this. So just a few features of the FlowUV device. As we said, very compact design. This instrument here is 17 centimeters square. It's really light, portable. We can move that around the laboratory. It has a powerful xenon lamp. This is synchronized with the detector. The xenon lamp we use is good for 10 to the 9 flashes. And we've calculated 24-hour continual use. This lamp will last for about 10 years. So you'll never have to change the light source. Along with the intuitive control software that we have a full spectrum of, pardon the pun, a complete list of external command protocols. So if you wanted to integrate this device into third-party software or into another process, that's all readily available for us as well. As I said, we can supply this with a range of accessories. We have a wide spectral range. And one of the nice features of our own control software is you can monitor up to 4 wavelengths at any point. So that's enough about the device. We really want to talk about why and how it's being used. So as we're going to be talking about continuous flow chemistry applications, I just wanted to highlight a few of those and the advantages and benefits that it can offer for this type of synthetic technique. So this allows us real-time reaction progression, or to monitor real-time reaction progression, and we can see those different changes in concentration, for example, within our experiments. We can use this for both process understanding, so reaction understanding, but also reaction optimization and development. We can monitor our reaction conditions, whether that is resonance time, stoichiometry, temperature, etc., without interrupting our experiments. With an inline flow cell coupled to the detector, we reduce manual sampling as well. And that has lots of advantages. It minimizes offline sampling, reduces contamination of our samples, improves reproducibility, and lowers the time in our analytical workflow. We don't have to move from lab to lab to find analytical equipment. It can harness safer and more reproducible workflows. So that remote monitoring allows those experiments to be seen, to be observed, without any direct exposure to the hazardous environment for sampling, etc. And as we'll see in the next few case studies, that analytical insight, that continuous analytical insight with continuous data collection really enables process observation. We can use this for PAT as well. So this is where that process deviation comes from. We can see any changes in our reaction continuously. So enough of me. Hopefully that was a good introduction into the advantages that we'll see. So really to demonstrate how inline UV phys monitoring supports these real world applications, I'd like to invite our first guest speaker, Dr. Ferdas Parveen. Ferdas is looking at using inline detection, specifically for porphyrin applications. So I will pass over the floor to Parveen.
Thank you, Andrew. I'll share. So, can you see my slides?
Yes.
Thank you, Andrew and Asynt, for your kind introduction and giving us opportunity to present at this platform. So today I will talk about our recently published research on continuous flow synthesis of meso-substituted porphyrins with inline UV vis analysis. Just a minute. Yep. So moving forward, I will talk about what are the differences between batch and flow. We have talked a lot about flow, but I would like to give a brief introduction about batch and flow. So in batch setups, reactants are added and they are allowed to react for set period of time, and products are isolated discretely. But in flow, reagents are pumped into the tubes and reagents react in these tubes. These tubes can be heated or cooled, and products are collected continuously. So typical flow reactor consists of different parts. It contains pumps which are used to pump different reagents. These reagents mixed in a T mixer or Y mixer, and it passed through a reactor. This is the zone where reaction happens. The two reagents can mix together and react, and reactors can be heated or cooled. And the outlet stream passed through a back pressure regulator. This back pressure regulator is required to maintain the upstream pressure, and this allow us to heat the solvent well above their boiling point. The reaction mixture can pass through the inline analytical UV or any PET analytical techniques to monitor the reaction mixture, and the product or reaction can be collected continuously. Further, there are different types of reactor depending on their dimension and application. Chip reactor, it offers best heat and heat transfer properties because it has very narrow internal diameter, which ranges from 250 to 800 micrometer. But the throughput through the chip reactors is quite low. So in most of the synthetic labs, you can find the coil reactor, which has a diameter from 0.01 inches to 0.125 inches. These reactors can be heated and cooled when required. CSTR is continuous stirred tank reactor. They are the series of tank reactor. The outlet of one of the reactor becomes the inlet of the another reactor, and so on. With this, it provides better mixing. It can handle slurries, and they are easy to scale up. The example is F reactor from Asynt. Further, you can have packed bed reactor. They are good for catalysis application, especially for heterogeneous catalyst. You can pack your material inside this omnifit column, and it simulates very high effective molarity of catalyst, and they are easy to scale up as well. And all these reactors can be found from Asynt. What are the advantages of flow? So moving from batch to flow, it offers faster and safer reaction. Like for example, in this case, the cage is forming in 5 days at room temperature in DCM, but in flow, you can heat it up to 100 degrees C, which is very difficult to heat DCM at 100 degrees C in batch. And it reduces the reaction time from 5 days to 10 minutes. This is all possible because you can pressurize your system very well in flow. Further, flow offer better heat and mass transfer as well as mixing. You can put the heat inside the reactor very fast, or pull out the heat from the reactor in a fraction of seconds. This is possible because for the same volume in batch, you can have a wall area of 4 centimeters square, whereas the area increases to 100-fold when you move to tube reactors. So this is how it pull out or push in the heat very fast during the reaction. Further, flow offers increased selectivity in the system. This is the thermal distribution in batch and flow. You can see the thermal distribution in case of batch is quite wide. So reagents can go into undesired pathway as well as, can go into undesired pathway alongside the desired pathway and reduce the selectivity of the final product. Whereas in flow, you can maintain the thermal distribution in the flow, in the reactor, and your reagent will only go through a desired pathway and increase the yield of your process. Further, flow can be easy to scale up. You can increase the dimension of the reactor without changing the reactor characteristics. And they are easy to automate. You can have multiple inline, at-line, and online techniques. My friend Harvey will talk more about inline, at-line, and online techniques in his presentation. And the data obtained from these techniques can be pulled into a single PC, and using the different algorithm like Bayesian optimizations, NOPFET, you can self-optimize your full setup. That can increase the safety, sustainability of your processes. So porphyrins are heterocyclic macrocycles. They have applications in various processes like thermodynamic therapy, energy production, cancer treatment, artificial photosynthesis, mediator, and catalysis. So porphyrins are formed by the condensation of pyrrole and aldehyde in the presence of acid known as trifluoroacetic acid, fluoroacetic acid, and then it gives an intermediate called porphyrinogen. Porphyrinogen on oxidation in the presence of chloranil gives mesoporphyrin. But as always, chemistry not always happen in a single direction. There are chances of side products. These meso-substituted porphyrins can further get protonated with the residual acid present in the reaction mixture to give you protonated porphyrin. And pyrrole can undergo polymerization to give polypyrrole. So these side reactions will reduce the yield of our desired product mesoporphyrin in the batch. Further challenges in porphyrin synthesis are they offer low yields. They are often require high dilution because otherwise if the concentration is high, it can lead to polymerization of the pyrrole. It is difficult to monitor the intermediate step, that is the yield of porphyrinogen and oxidation timings. Further, varied reaction times for different aldehydes. It can vary from seconds to days for different substrates, limiting to scale up because of the high dilution, and residual acid protonates the porphyrin. So to solve all these challenges, we went to flow. So best reported literature in batch found to be from Lindsay, where he has used dichloromethane and chloroform as reaction solvent and did the reaction at 25 degrees C in 2 steps. That means separating the condensation and oxidation steps and using parachloranil as an oxidant, and found the yield as 38%. The first continuous flow reported literature is from Momo, who used Gonsalves condition and used propanic acid and nitrobenzene as reaction medium, and propanic acid as a catalyst, whereas nitrobenzene act as an oxidant. They did the reaction in a single step in the single reactor, and they found the yield as 31%, which was which is lower than the batch Lindsay condition. So this Gonsalves conditions are not competitive, like they are not useful for aldehyde substrate which have sensitive functional group. So we decided not to use propanic acid or nitrobenzene, rather use Lindsay condition and translate that into flow. We set up a reactor having 2 pumps which can pump aldehyde and pyrrole together in a reactor, one where condensation happens and then intermediate porphyrinogen will get oxidized by addition of chloranil in the reactor 2. The reaction mixture is collected in a round bottom flask, which already contains triethylamine as a quench. This reaction mixture then purified on a slick up plug to get the purified porphyrin. As you all can see on the slick up plug, you can see a green color and a black color at the top. So to further understand the system, we optimized different reaction conditions, different reaction parameters, and we found that increasing the concentration from 0.018 to 0.025, we found there is a reduction in the yield. This might be the case that higher concentrations are causing the polymerization of pyrrole and reducing the yield of the porphyrin. Further, we studied the effect of residence time onto the yield. It has a positive effect going from 17 to 20 and 25. It increased from 26 to 32.5%. And the temperature has a positive effect onto the yield of porphyrin. 25 to 35, there is an increase in the yield, but not much, 31 to 35. But further increasing to 50 degrees, it further reduces the yield. That means at higher temperature, there might be chances of site reactions taking place as compared to the reaction to go into the desired pathway. So we decided to stay at 25 degrees because there was not much difference between 31 and 35% yield of the porphyrin. To test the equivalence of the catalyst, we varied it from 2 to 2.5, and there was a positive effect on the yield of the porphyrins. So with this, we found the best optimized conditions were 0.02, 20 minutes residence time, and 25 degrees temperature in the coil 1, and 2.5 equivalent of catalyst, giving us 42.3% yield of porphyrin. So we decided to add the neutralization as well in line and telescoping the process rather than collecting the reaction mixture in batch and purifying it. We added inline neutralization, and we monitor the reaction with the Asynt FlowUV. With this, we found while monitoring the reaction mixture, we found we were getting lots of peaks. And to understand the peaks at 418, 438, 482, we run the standards of porphyrin and protonated porphyrin, and immediately we figure out like 438, which is the major peak in the system in the reaction mixture, is coming from protonated porphyrin, and 418 is for the porphyrin. To further find out what is 482, we put a Unix's we put a Asynt FlowUV just after the reactor 1, and found that 482 correspond to the intermediate porphyrinogen, and the peak at 400 is a peak which comes from different concentration of porphyrin. If you have highly concentrated porphyrin, then you can get a peak at 400, but if you have a dilute sample, you can get a peak at 418. Also from this spectra, you can see at 0.9 microliter per ml of triethylamine quench is not enough to deprotonate the porphyrin because we are getting the major peak at 438. So we adjusted the volume of triethylamine to 100 microliter per ml, and the peak for the protonated porphyrin was reduced, like we completely neutralized the reaction mixture. So with this, we were able to improve our yields of porphyrin by complete neutralization of the protonated porphyrin. And for the quantification of the yield from the UV-Vis line analysis, we ran the standards for different porphyrins between the concentration varying from 9.3 microgram per ml to 46.5 microgram per ml, and plotting the standard calibration curve. This curve followed the Lambert-Beer's law as suggested by Andrew earlier in his presentation. So this the concentration is absorbance is a function of concentration. So the lower is the absorbance, more will be the concentration. So we did compare the two processes, which batch neutralization to inline UV-Vis analysis. So the yields obtained in batch neutralizations are absolute yields of the porphyrin. When we did the silica plug purification, we got the compound, we dried it and weighed it. These are the yields from batch neutralization, whereas in percentage yield in line UV analysis are analytical yield. These yields we got from the external calibration curves for each porphyrin. From for the two different processes, batch neutralization and inline UV vis analysis, we found that there is not much difference in the standard porphyrin. The yields were similar, but in case of functionalized substrate like thioether and silyl alkyne, there was a large difference in the yield found from inline UV vis analysis and batch neutralization. This suggested that definitely we are forming large quantities of porphyrin in the reaction, but when we are neutralizing them in the batch and purifying them on a silica plug, the yields are reducing because these substrates are not stable, they are decomposing over time. So to further improve this process, we suggest like we should add inline purification method so that we can further improve the process of the system, and further adding multiple collecting the data at multi-point in the reactor would be essential if we want to fully understand the process. That will be covered up by my colleague Harvey in his slides. So with this, I would like to thank and showcase our MIF Flow Center, which we have at University of Liverpool. We do have multiple flow reactors and analytical probes. Uh, we can provide consultancy, we can provide training and work on a funded collaborative project. We work on a flexible access model. If you like to test your chemistry with us, please reach out to us. We will be able to help you with your chemistry. And we provide case studies to improve the efficiency, selectivity, scalability, safety, reproducibility, and sustainability of the system. We do also provide proof of concept data for larger scale activities. At Flow Center, we have different flow reactor, including the F reactor from Asynt, and we have different analytical probe, Asynt FlowUV, Mettler-Toledo IR, different LCs and NMR. So with this, I would like to thank Slater's group and especially Henry and Harvey, who helped me accomplishing this project. And I would like to thank Royal Society for providing the funding and Material Innovation Factory University of Liverpool for providing the facilities. And if you want to reach out to us, here are my link and QR code. Thank you. And we studied the effect of residence time onto the yield. It has a positive effect going from 17 to 20 and 25. It increased from 26 to 32.5%. And the temperature has a positive effect onto the yield of porphyrin. 25 to 35, there is an increase in the yield, but not much, 31 to 35. But further increasing to 50 degrees, it further reduces the yield. That means at higher temperature, there might be chances of site reactions taking place as compared to the reaction to go into the desired pathway. So we decided to stay at 25 degrees because there was not much difference between 31 and 35% yield of the porphyrin. To test the equivalence of the catalyst, we varied it from 2 to 2.5, and there was a positive effect on the yield of the porphyrins. So with this, we found the best optimized conditions were 0.02, 20 minutes residence time, and 25 degrees temperature in the coil 1, and 2.5 equivalent of catalyst, giving us 42.3% yield of porphyrin. So we decided to add the neutralization as well in line and telescoping the process rather than collecting the reaction mixture in batch and purifying it. We added inline neutralization and we monitored the reaction with the Asynt FlowUV. With this, we found while monitoring the reaction mixture, we found we were getting lots of peaks. And to understand the peaks at 418, 438, 482, we run the standards of porphyrin and protonated porphyrin, and immediately we figure out like 438, which is the major peak in the system in the reaction mixture, is coming from protonated porphyrin, and 418 is for the porphyrin. To further find out what is 482, we put a we put a Unix's, we put a Asynt FlowUV just after the reactor 1, and found that 482 correspond to the intermediate porphyrinogen, and the peak at 400 is a peak from which comes from different concentration of porphyrin. If you have highly concentrated porphyrin, then you can get a peak at 400, but if you have a dilute sample, you can get a peak at 418. Also from this spectra, you can see at 0.9 microliter per ml of triethylamine quench is not enough to deprotonate the porphyrin, because we are getting the major peak at 438. So we adjusted the volume of triethylamine to 100 microliter per ml, and the peak for the protonated porphyrin was reduced, like we completely neutralized the reaction mixture. So with this, we were able to improve our yields of porphyrin by complete neutralization of the protonated porphyrin. And for the quantification of the yield from the UV-Vis line analysis, we ran the standards for different porphyrins between the concentration varying from 9.3 microgram per ml to 46.5 microgram per ml, and plotting the standard calibration curve. This curve followed the Lambert-Beer's law as suggested by Andrew earlier in his presentation. So this the concentration is absorbance is a function of concentration. So the lower is the absorbance, more will be the concentration. So we did compare the two processes, which batch neutralization to inline UV-Vis analysis. So the yields obtained in batch neutralizations are absolute yields of the porphyrin. When we did the silica plug purification, we got the compound, we dried it and weighed it. These are the yields from batch neutralization, whereas in percentage yield inline UV analysis are analytical yield. These yields we got from the external calibration curves for each porphyrin. For the two different processes, batch neutralization and inline UV-Vis analysis, we found that there is not much difference in the standard porphyrin. The yields were similar, but in case of functionalized substrate like thioether and silyl alkyne, there was a large difference in the yield found from inline UV-Vis analysis and batch neutralization. This suggested that definitely we are forming large quantities of porphyrin in the reaction, but when we are neutralizing them in the batch and purifying them on a silica plug, the yields are reducing because these substrates are not stable, they are decomposing over time. So to further improve this process, we suggest like we should add inline purification method so that we can further improve the process of the system, and further adding multiple collecting the data at multi-point in the reactor would be essential if we want to fully understand the process. That will be covered up by my colleague Harvey in his slides. So with this, I would like to thank and showcase our MIF Flow Center, which we have at University of Liverpool. We do have multiple flow reactors and analytical probes. We can provide consultancy, we can provide training, and work on a funded collaborative project. We work on a flexible access model. If you like to test your chemistry with us, please reach out to us. We will be able to help you with your chemistry. And we provide case studies to improve the efficiency, selectivity, scalability, safety, reproducibility, and sustainability of the system. We do also provide proof of concept data for larger scale activities. At Flow Center, we have different flow reactor, including the F reactor from Asynt, and we have different analytical probe, Asynt FlowUV, Mettler-Toledo IR, different LCs, and NMR. So with this, I would like to thank Slater's group, and especially Henry and Harvey, who helped me accomplishing this project. And I would like to thank Royal Society for providing the funding, and Material Innovation Factory, University of Liverpool, for providing the facilities. And if you want to reach out to us, here are my link and QR code. Thank you.
Thank you, Parveen. That's an excellent illustration of how inline detection can help, both in identifying and monitoring intermediates, adding to telescope processes for inline quenching, and using UV-Vis analytical techniques to identify concentration of samples. So our next speaker in this webinar is Harvey West. Harvey is a PhD researcher in the same group, Anastasis group in the University of Liverpool. And Harvey will be continuing what we've seen with Pardus this morning. So Harvey, over to you.
Brilliant. Let me just share my screen. Great stuff. There we go. Let's get my favorite laser pointer out as well. So first off, let me apologize because there's probably going to be a little bit of overlap between the things that Andrew's discussed and also Firdaus today. We've all got our own axis to grind, and as a flow chemist, I know what I'm here to talk about today. So this talk's titled Beyond the Flask, and as a flow chemist, I'm desperately averse to working with sticky glassware and stuff like that. So as Andrew's mentioned, I'm a doctoral researcher in flow chemistry within the Slater Group at the University of Liverpool. So why might you want to do some flow chemistry? Flow chemistry offers a number of different advantages over traditional batch synthesis, summarized in this lovely graphic image over here that I wheel out for most of my presentations. But they're also listed over here on the left. We've got opportunity to have enhanced control over our systems, operate in a much safer way than we might traditionally through the use of much smaller reactive volumes. We have excellent control over our heat and mass transfer rates. And often we're able to run experiments in a much more reproducible and consistent fashion than you might see with a round bottom flask. For any flow chemists in the room, you're probably wincing ever so slightly at this point, that there are a couple of invisible asterisks there, but these systems are often quite easy to scale, either by numbering up and running a number of flow reactors, or by scaling up a reactor and having a bigger internal volume, larger tubing, that kind of stuff. We're also able to access challenging reaction conditions, often far exceeding the boiling point and pressure conditions that you'd be able to with traditional batch synthesis. And we're able to reduce our waste and improve our sustainability, which is ever such an important aspect of modern chemical and green research. Down here in my favorite purple box at the bottom are my three key aspects of flow chemistry that really resonate with my own personal research. And that's first and foremost the fact that flow chemistry is easily integratable with automation and closed loop optimization strategies. It's also very easy to introduce either inline or real-time analysis as well. And all of these advantages give us a much greater increase in our understanding of our processes, whether we're looking at steady state behavior, transient states where we adjust our reactor conditions from one level to another and observe the change in between, or if we just want to monitor our reaction progress in real time. So what methods of analyzing flow experiments do we have available? There's four broad categories that we use to discuss this. First and foremost is inline analysis, where we analyze our reactive flow directly. We have online analysis, where we divert a portion of our reactive flow, analyze it, and then either return it to our reaction stream or, as is commonly the case, discard it. We have at-line, where samples are manually withdrawn and analyzed at a device nearby, commonly benchtop spectrometers or other such devices. And finally, we've got the one that I'm sure is very familiar to people in the room, where we perform our analysis often much later using whatever flavor of analytical chemistry or device that fits our chemistry specifically. So why exactly do we like to use inline analysis as flow chemists, and why do I prefer to use inline analysis? We've got access to real-time reaction monitoring, and we can also detect our transient behavior, as I mentioned previously, capturing startup effects and transitioning from one set of reactor conditions to the next set. We're able to reduce our sampling and our manual intervention, processes, which greatly accelerates our workflows in a lot of cases. Something that may be of particular interest to those in say, the pharma fields, or people working with expensive or dangerous chemistries, is the fact that these are non-destructive analytical methods as well. We've got access to a significantly higher data density as well, and that can afford us an awful lot of data to do number crunching offline or even real time, in informing our future decisions much faster. We've also got the opportunity for earlier fault and failure detection, which when working with flow chemistry can be absolutely life-saving, particularly when you can notice the fingerprints of blockages forming, concentration changes, or instability in our system or our process. Just to bring back my favorite purple box, these are the key elements that really align most closely with my current research. Often with the flow chemistry, we tend to take our total residence time of our system and then add a comfortable safety margin on the end, typically 25 to 50% extra time, and then fly under the assumption that our system is at steady state. When deploying inline analysis, we don't need that level of assumption. We can see that we are truly there. We're also able to achieve faster optimization of our process, gain significantly improved process understanding, allowing us to probe into chemical kinetics, our reaction progression, or our system behavior. And inline analysis also gels really quite well with automation and self-optimization workflows, which are really a hot topic within flow chemistry at the moment, particularly when combining with AI, for example. And this comes back to the idea that you really can't control what you can't see. And inline analysis gives us that looking glass into the chemical unknown. So I'm secondarily a porphyrin chemist, something that gives me a deep synergy with the lovely Kerry from Asynt. And I work predominantly with a Lindsay method transitioned into flow. Summarized in this lovely simplified reaction scheme here. This is a two-step process where first we have a reversible acid catalyzed condensation reaction occurring between an aldehyde and a pyrrole. And this has been reported for many aldehydes, particularly aryl aldehydes. And finally, an oxidation step, which converts our porphyrinogen intermediate species, which is often quite hard to isolate and analyze in batch, into our final porphyrin product. Shown just here is a summary graphic for one of my earliest workflows, where we deployed this lovely telescope synthetic process, focusing mostly on performing isolated yield calculations from a round bottom flask and column chromatography, but also including an awful lot of very time-consuming offline LC-UV analysis, all of this feeding into a design of experiments optimization strategy. So I've shown you a few reactor schematics so far, but you might be curious to see exactly what a flow setup looks like in reality. We've got our 4 reactant flows labeled A to D here in the lovely starting material bottle sat atop the reactor, delivered by 4 pumps, and we have access to a variety of different pump styles, but I in particular was using LC and peristaltic type pumps. We use 3 reactor coils across a telescoped increasing volume, and these were made of PFA, giving us a maximum operational temperature of about 150 degrees C and a maximum of 10 bar. At the very end of our system, we have a back pressure regulator, ensuring that we don't start to boil our solvents and ruin our reaction. And for this workflow in particular, it was mostly operated at 7 bar. Now, it'd be remiss of me at this point to not highlight that while I used initially a Vaportech system, there are a great deal of different reactor configurations available and currently on the market. The Flow Lab from Asynt itself provides really quite exceptional fine control over flow rates and therefore your residence time by the use of some excellent LC style pumps, but also through the use of stainless steel and Hastelloy and some very interesting novel reactor designs, you can gain access to a really quite broad range of reaction temperatures, down to the low 50s and negative 50 and 60 degrees sort of point, all the way up to kind of the hundreds of degrees C. And systems like this are often really quite well designed to allow almost immediate and really quite facile integration with inline analysis. As my colleague Firdaus mentioned as well, we can work with devices called continuous stirred tank reactors, or CSTRs, where through the use of wider bore tubing and a cascade of small tank reactors, we can achieve a really quite tight control over our residence time distribution and negate some of the common issues with flow chemistry of blockages or solid materials, say, crashing out in solution. So let's take a moment to look at some of my my porphyrin specific data from my day-to-day workflows. As I mentioned previously, flow chemistry is incredibly data rich, and this gives us the opportunity to probe in real time, particularly with a telescoped process, each discrete step in our reaction. What you can see just here is real data from our porphyrinogen intermediate species taken directly after our first coil, our condensation step, and some continuous inline analysis taken after our oxidation step, and also finally after our quench step, giving us our H4 TPP2+ species and our final porphyrin free base product. Down at the bottom, you can see some really quite satisfying normalized spectra for each of these, where we can even see the appearance of our very classic porphyrin Q bands. And working with flow chemistry, we actually have to adopt a pretty unique mindset. And that's this idea that we're dealing with a spatially resolved representation of reaction time, whereby each point within our telescope system acts as if it's suspended in time. Not unlike the idea of looking up at the night sky and appreciating that we aren't viewing the universe as it currently is, but gaining an insight into galactic history. So let's have a look at some real inline reaction data. We can take away a couple of immediate, easy bits of analysis from looking at this. First and foremost, this was from nearly 4.5 hours worth of reaction data. And it's not unheard of within the field of flow chemistry to run reactions ranging all the way from a few seconds up to, in some extreme cases, days long. The second thing that we can see is the appearance of what we refer to as the steady state conditions, indicated by this lovely flat profile for each of our responses. However, if we zoom into that information and focus on our most intense response at 515 nanometers, despite the distant view that these may be lovely flat lines, we can see that our system never truly achieves a steady state condition. And therefore, it would be unwise to treat any one of these individual flat portions as an accurate data point. We were able to trace this back in the end to system instability arising mostly from some pump performance issues and some really quite warm temperatures in the lab during last summer. We can go beyond inline analysis and just constantly monitoring points, and we can also deploy sample loop style diversion of aliquots, giving us our lovely, beautiful, integratable and reproducible peaks of our porphyrinogen intermediate species shown just here. So let's take a quick look at the FlowUV spectrometer itself, a daily workhorse for myself in the lab. Up here is the device, and down here is the application that I predominantly use to control it. Immediately, we can see that we have access to a really quite wide dynamic range from our pulsed xenon source. And this is somewhat unique, given that the majority of UV spectrometers that I've used in the past rely on a dual source system with a tungsten halogen lamp covering the majority of the visible portion, and a deuterium lamp covering the ultraviolet region. This is really quite helpful for us because it avoids some of the issues we see with deuterium lamps having far too much intensity in the ultraviolet region. We're able to dynamically adjust the strobe power and avoid issues caused by oversaturation or negate issues that we see in telescoped processes, in particular of continuous dilution of our analyte. Our data is plotted as a function of time, which is absolutely perfect for us to be able to monitor our steady state. And as Andrew pointed out, we can monitor 5 wavelengths simultaneously and adjust these on the fly, giving us a unique opportunity to kind of shift our looking glass to where we need to be at that current time. We're also able, through the use of switching valves, to purge our flow cell and pump our blank solution through, comparing our current blank measurement to our recorded blank measurement shown in red, allowing us throughout the day, and this is particularly helpful for long experimental runs, to assess if there has been any deviation, because sources heat up, as do detectors, but also an awful lot of ambient conditions in your workspace can change throughout the day as well. Temperature, pressure, transient light, for example. Finally, we've got access to a mathematical smoothing filter, which allows us to deal with perhaps quite noisy data, and also an exposure timer, again, giving us the opportunity to deal with issues such as oversaturation of our detector. And finally, this is particularly useful for myself and my workflows with longer reaction periods. We can adjust on the fly our log interval, where we're commonly interested in gathering a much higher rate of data when we're dealing with transient conditions or on the run up to our steady state. But given we can produce tens to hundreds of gigabytes worth of data, it's often helpful once we've hit those steady state conditions to dial that back and maybe measure, every 10, every 100 seconds rather than a data file per second. So let's take a look at just a hint of my future plan. Obviously, as I've already alluded to, we're aiming to achieve self-optimization and closed-loop operation of our flow experiments, whereby gathering this multi-point analytical data, we can automatically process it, feed it into an optimization algorithm, and spit out a new set of reaction conditions, rinsing and repeating until we achieve, ideally, an optimum in say, yield or selectivity or reagent use, temperature, those kind of things. But we can go further, and we can apply this body of knowledge to alternate workflows and different chemistries, where we're actively working on analyzing other macrocycles, but also, and most interestingly to myself, multi-step and reversible processes, because these can be exceptionally challenging to probe when working with traditional batch processes. So in conclusion, I'd like to hope that I've broadcasted the utility of flow chemistry to the audience today, alongside highlighting some of the key advantages and opportunities for, in particular, inline UV analysis, but just UV analysis in general, and merging that with flow chemistry setups. I presented a small snapshot of my current porphyrin research with some more of my real data just here, and given a little sprinkling of a hint at my future plans. And I would encourage you all to please watch this space for upcoming publications from myself, Firdaus, and the wider Slater group. So thank you ever so much for taking the time to attend today and listen to my talk. I personally want to thank the lovely folk at Asynt. If you do have any questions, please feel free to ask in the chat, or if you'd prefer. I'm sure you're all pretty familiar with the fact that final year PhD students would absolutely love to talk the ear off anybody that even has a tangential interest in their research. So feel free to drop me a direct email or connect via LinkedIn if you'd sooner. Thank you ever so much. I'll hand back over to Andrew.
Thank you, Harvey. Fantastic, another fantastic talk. two very similar but very different outputs. We've seen some synthetic utility, lots of advantages of flow chemistry. I'm a flow chemist myself. I understand that the yields highlighted are very good for porphyrins, not being a porphyrin synthesis myself, but thank you very much. We've seen the application for steady state optimization, process optimization and understanding, but also how these techniques can be implemented into self-optimizing systems as well. So just as a conclusion, I'm just going to share my screen one more time before we take Q&As. So we've seen how UV vis monitoring, inline UV vis monitoring really matters for flow chemistry. It's a very powerful tool. That real-time analysis, as we've seen, as I've just stated, can give us real deep understanding of our reactions and our reaction progressions. And you can see we can put that anywhere in the flow process, in that fluidic process, so we can understand intermediate formation, product formation, and optimize our conditions around that. And again, two excellent case studies from our guest speakers today. So for want of time, I'm going to open the floor to any questions. Hopefully you've dropped some questions in the chat function. If you have any questions relating to the device itself or the research that you've seen, please feel free to drop the questions in. Catherine will be helping me out asking those. If we run out of time in this session, we'll endeavour to answer those questions for you. So, the floor is yours. Catherine, do we have any questions?
I can see two questions in the chat. I can answer about the peak overlap and how would you mind answering controlling the pump where Python?
Yep.
Yes. So
Yes, sorry, feel free. Yeah.
Luckily, in our case, we were not seeing any overlapping of the signal. I can share my slides where we run the metrics. So here are the slides. So we ran individual component and as a matrix, and we didn't see any peak overlap. So we were lucky in that way. But if by any chance, if you get peak overlapping, there are different methods like PLS or deconvoluting the peak. You can use that. Thank you.
Okay, thank
Harvey,
you.
over to you.
Just to also support Fidausa's answer there, given that you can deploy sample loops, for example, to divert your reactive flow, there's nothing stopping you if you have overlapping peaks directly integrating a flow chemistry system with either HPLC or GC, so that you can deconvolute any peaks there. There are also a number of really quite helpful mathematical approaches that you can take, such as multivariate peak analysis, I think it's called. So you do have a lot of opportunities if you do have overlapping signals, for example. To answer the question relating to how we control our system, I day-to-day often work with a VaporTech system. They provide a full Python-based API to control the reactor and in particular the pumps. I do also routinely work with a series of Masterflex pumps, and again they provide API access, but you can also control an awful lot of devices just via serial comms. C++ is a common coding solution to control these devices.
Yes.
It really will depend on the specific manufacturer of those devices.
I would just point out, just to add to that the FlowUV device has a full Python script for integration with any flow chemistry system. Here at Asynt, all of our flow chemistry apparatus is controlled by direct IP, so very easily integrated and communicated with. Have a question here about the lamp, about calibration. So one of the nice things about these instruments is once they're factory calibrated, there are no moving parts. So that calibration is continuous throughout the lifetime of the system. There's a question here about the temperature range of the probes. So I can answer that, but our two speakers here have obviously been running their flow chemistry at temperatures. And what was the temperature? 150 degrees were you operating at?
That's one of the maximums that we can go to with polymer tubing. One of the things to bear in mind is, particularly when you're working with very narrow bore tubing, is by the time your flow has reached your flow cell, it can have dropped in temperature quite significantly. But we've seen no real issues with analyzing higher temperature flows.
Yeah, I would point out that we would rate our inline flow cell to 150 degrees. And that's just the limitation of the material that we use, PFA tubing. All right, another question here. So how do you measure the concentrations of reaction components when the peaks overlap? How do you resolve the peaks for calibration concentration measurements? Well, I guess that question comes with the ability to monitor multiple wavelengths at once. If you have shoulders on your spectrum, you can use that facility, if there is a definition between the peaks, to monitor the relative intensity of the overlaps.
I can answer this question. What is the accuracy of analyzing the concentration?
Sorry, I'm scrolling through.
If peaks are not overlap, we ran triplicates of the reaction and we found that the variation varies from 5 to 10% error bar. So it was quite under the accuracy, I would say quite accurate.
Well, we are almost at the end of our time. So I would just like to thank our guest speakers again. Thank you for two fantastic presentations. Hopefully this webinar has been useful, that you've learned something about our instrumentation and something about porphyrin synthesis and how inline UV analysis can really help, and especially in those flow chemistry applications. So thank you all for attending. If you have any further questions or you would like to know more about the Asynt FlowUV spectrometer, please drop us a line and we'll be happy to speak to you again. So thank you, Fergus, thanks Harvey, and thank you all for attending.
Thank you.
Thank you, everybody. Bye now.
Bye.
Bye.